I welcome all the students to Pune College of Arts, Science and Commerce, Camp Pune 1. I teach FYBSc and FYBA, the subject statistics. The course name is Discrete Probability and Discrete Probability Distributions. Myself, I am Dr. M.B. Pathan. In last lecture, we have seen 4 definitions related to univariate probability distributions. Definition number 1 is about random variable. A real valued function defined on a sample space to the subset of real numbers is known as a random variable. Second definition is about discrete random variable. The random variable taking values either finite or countably infinite is known as discrete random variable. Third definition, probability mass function. The function, say capital P, defined on each value of capital X such that P of xi greater than equal to 0 for every I 1 to n, and summation P xi should be exactly 1. Then such function capital P is known as PMF, probability mass function. This concept is exactly parallel to the topic which I taught in previous chapter under the heading of probability model. In case of probability model, function defined on a sample space, whereas probability mass function defined on the values of random variable. The last definition what I had given to you is probability distribution. The ordered pair values of random variable with respective probabilities is known as probability distribution. Today, we are going to see different examples which will try to explain you all these 4 definitions what we covered in previous lecture. Just now I told you about probability distribution. Probability distribution is ordered pair values of random variable x with respective probabilities. You can represent probability distribution in a tabular form like this. X taking values particular x1, x2, dash dash xi, dash dash xn. For x1, what is the chance to occur to take the value by random variable x is p1, that is the probability of x. So such table is known as a probability distribution of random variable x under study. Today, what we are going to do, we'll try to understand all these 4 concepts with simple example. And then I will tell you why we study probabilities with the help of random variable rather than sample space. Let us take one example. A fair coin is tossed 3 times. Obtain the probability distribution of getting number of heads. Now we have seen such example in previous chapter also. Here the word fair means each outcome, excuse me, वालेकुम, आप लेट ज्वाइन होते, जल्दी ज्वाइन होना चाहिए ना, ठीक है. ट्राई करो। हाँ, अच्छा, क्या नाम? हाँ, बल। हाँ हाँ, ओके ओके जी। So let us see the example. A fair coin is tossed 3 times. The meaning of fair is when you toss a coin, there are two outcomes. You either get head or tail. But chance of getting head is equal to chance of getting tail, then corresponding coin is called as a fair coin. From previous chapter, we know if I toss a coin 3 times, omega has a 8 element. And we can find the probabilities for each and every possible event by using probability based on the classical definition with the help of sample space. Now we'll try to see what is the difference. Here what we want to develop probability distribution for number of heads. So we want to get this table for this corresponding experiment. See the procedure. Solution, you have to begin with random experiment on the top. Tossing a fair coin 3 times. So we have omega with 8 elements. That is, everybody knows it. Therefore, small n stand for how many outcomes in the experiment. Answer is 8. Now I define a function you may call as a relation on this sample space. What is a relation? A relation is what is your interest. You want to find probability distribution for getting number of heads in your experiment. So I define my relation, my random variable, you may call function, as capital X equal number of heads in omega, ultimately in random experiment. So I define this X on each element of omega. See what will happen. X on W1, first sample point, and first sample point is HHH. So X of HHH is equal to 3. Why it is 3? Because X is a counting variable. We are counting number of head. So if you count here number of head, they comes 3. Similarly, I go for X on second sample point equal to X of HHT, and now here X takes value 2. X of W3, X HTH, again 2. XW4, XTHH, again 2. XW5, XHTT. Now here only one head. So X will take value 1. XW6, XTHT 1, XW7 equal XTTH is 1. Now here what we did, we define X on every element of omega. XTTT, there is no head, so it takes value 0. 1 is wrong, it is 0. This is correct. So it is 0. Now you can see by this procedure, your outcome of experiment transfer to the real values. And whenever I want to write as a range set, we have a range set, capital X, Rx as a notation, curly bracket, minimum 0 and maximum 3. Here 3 repeat once, 3 repeats thrice, 2 repeats thrice, 1 repeat once, 0 repeat once. But when you write a curly bracket collection, the numbers are not repeated. Distinct values taken under the range set. Now up to here, what you understand? You understand first two topics. Concept of random variable and concept of discrete random variable. What is a random variable? It is a relation defined on a sample space to the subset of real values. When it will be discrete, if it takes finite values or it takes countably infinite values. So here X takes only 4 values. That's why this random variable X is called discrete random variable. I think you clear the concept of random variable and discrete random variable with this simple example. What we did, we defined this relation on every element of sample space. H transfer to 3, this 3 element transfer to 2, this 3 element transfer to 1, and this last element transfer to 0. So this procedure of getting the real values for given outcome of the random experiment is known as random variable. And if your random variable taking a discrete value, separate values, it will be named as a discrete random variable. Now, what is the next step? Next step is for every X, how much chance to get? That means X taking value 3 with how much probability? X taking value 2 with how much probability? That is the next step to get a probability distribution. To get probability distribution, we should find the probability for each value of X. Let us proceed. P1 equal probability X taking value 0. Answer is 1 by 8. How it is 1 by 8? In omega, total element are 8. Out of 8, only one outcome takes value 0. That's why chance become 1 by 8. P2, second probability, equal probability X taking value 1. Answer is written as 3 by 8. Why 3 by 8? Again, the same interpretation. Omega has 8 elements. Out of 8, 3 elements gives value 1. What are that 3 values? These are nothing but these 3 outcomes where only one head is there. And that is why your probability is 3 by 8. P3 that is probability x taking value 2 equal to again 3 by 8. Omega has 8 element and we have 3 outcome which taking value 2 having 2 head, and that is written here HHT, HTH, THH, and that's why probability is again 3 by 8. P4 probability x equal to 3 is equal to 1 by 8. The reason sample space has 8 element. Out of 8, only one element takes value 3, and that is nothing but only first element has a 3 head. So this is the favorable outcome for 3 head, and that's why probability is written to be 1 by 8. Now to get the answer of question, what is the question? Question asks you, find the probability distribution of getting number of heads. So I will put this calculation in a table form. X taking values 0, 1, 2, 3. With probability for every value of x, x is 0 with 1 by 8, x is 1 by 3 by 8, x take value 2 by using probability 3 by 8, x takes value 3 with chance 1 by 8. If you make a total of these all probabilities, the total is 1. And therefore, this is nothing but probability distribution. This is the important condition to have a probability distribution. We seen third definition. What is the third definition? Probability mass function. Any function taking greater than equal to 0 values. All values are greater than 0. And if you make a total, total should be 1. So this condition satisfied. That's why this Px is known as probability mass function. Now you can say how it is probability mass function. It is the individual values. I can transfer these individual values in a function form. What is that functional form? Look here. Px equal 3 choose x half raised to 3 semicolon x taking value 0, 1, 2, 3. Let us verify this table by each value of x. Suppose I replace x equal to 0. What the answer you get? 3 choose 0. By combination it is 1. Half raised to 3 is 1 by 8. So I get this 1 by 8 value from this function. This is my function under study. If I put x equal to 1, 3 choose 1. If you apply the combination, 3 factorial divide by 1 factorial in bracket 3 minus 1, that is a 2 factorial. So 3 choose 1, answer is 3. Multiply half raised to 3 is 1 by 8. 3 multiply 1 by 8, result is 3 by 8 at 1. Now suppose I take x equal to 2 in this function. 3 choose 2, again answer is 3. Multiply half raised to 3 is 1 by 8, result is 3 by 8. Now I put the value of x at the last 3. 3 choose 3 is 1 by combination. 3 factorial divided by 3 factorial in bracket 3 minus 3 factorial is 0 factorial is 1. 3 factorial cancel with 3 factorial, result is 1. Multiply half raised to 3, that is 1 by 8. So what I want to tell you, I wrote these numerical values in the functional form. So this Px is known as probability mass function. Why? Yesterday we have seen, that means last lecture, any function having two conditions. Number one, function take non-negative values and total of all values should be 1. Both conditions satisfied here. And that is why this function is known as probability mass function. Now let us come to the topic. What topic? Why we study probability with variable. Does sample space is not enough? Answer is no. Sample space is not enough to study probability. What is the reason? The reason is very simple. If I toss a coin 3 times, I get 8 elements. I can write sample space, I can study probability. Suppose I toss a coin 4 times, I will write sample space with 16 elements. I can study probabilities. Suppose I toss a coin 5 times. How many outcomes will be there? There will be 2 raised to 5 outcomes. That means it comes 32. So as number of tosses increase, sample point outcome of the experiment increase. So it becomes difficult. To overcome this difficulty, we study probabilities with the help of functions, that is with the help of random variable. Now how this difficulty solve here? Very easily you can see this function. What these 3 stand? This stand for number of toss. A fair coin toss 3 times. So power coming 3 here and 3 here. Suppose I solve this question in general. A fair coin toss 12 times. Can you write probability distribution or not? Easily you can write. So this thing is not happening with sample space. Sample space has limitations. So if I repeat this question by asking a fair coin toss 12 times, find the probability of getting 3 head. So can you find or not? Easily you can find Px equal 12 choose x multiply half raised to 12 semicolon x takes value 0, 1, 2, 3 dash 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 up to 12. So if I want to make a general formula, suppose I toss a coin n times. So what is my function? Px equal n choose x half raised to n semicolon x takes value 0, 1, 2, 3 dash dash up to small n. Now you don't take this as only a tossing of a coin experiment. When we use such type of example in a classroom, it is a model now. You can apply this type of calculation in your real life for any experiment where a trial gives 2 outcomes. So tossing of a coin is a statistical model to apply in day-to-day life where experiment gives 2 outcomes in every trial. What are the examples? Suppose I study quality of a product which is manufactured by machines. So if I speak a quality, I say good quality, I say bad quality. So I can apply this model there. The result of examination, suppose there are 100 students in front of me and I want to study the pattern of pass and fail, so I can apply this model. So tossing of a coin is very good example to handle any experiment in the real life which provides two outcomes in every trial. Now I proceed ahead. Example 2 of similar nature but experiment is different. A pair means two, of fair means unbiased, dice is thrown at a time. So you have two dice, which is a fair, and you are throwing that two dice at a time. Question asks, find the probability distribution of sum of upper faces. Just like in previous example, number of head is recorded, that is X. In this experiment, you are recording sum of uppermost faces, how many dots are coming on first dice and second dice, you are making sum of that. And you want to develop probability distribution for this variable. Procedure exactly goes as example 1. Begin with random experiment, throwing of pair of fair dice. Therefore, we have omega. Everybody knows for this type of experiment, sample space has 36 elements that we have seen in very first chapter, sample space and events. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Like this, here you can write dot, 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 and you continue up to 6, 6. If you count these in every row, 6 elements. So totally, your experiment has 36 outcomes. N equal total outcomes of experiment. Let us define random variable in simple word as a relation on sample space. Capital X, be remember, random variable always denoted by capital letter. Sum of upper faces in omega, in other word, random experiment. Now I define this X on every element of omega. Now here I will not do as I did in example 2 because there are 36 elements. So by making a generalization, I write the range of X. Sum of upper faces, minimum sum will be 2, 3, 4, and maximum sum will be 12. You can see from a sample space, I'm making total of these 2 points. This one says there is 1 dot on first dice and there is 1 dot on the second dice. Sum is 2. Here sum is 3, 4, and go on like this. Maximum sum of variable is 12. So my variable range is minimum 2 and maximum is 12. Now to develop probability distribution, our next job is for every value of X, how much probability is there? That means X take value 2 with how much chance? X takes value 3 with how much chance, and so on. That we'll try to find out. Number 1, P1, first probability X taking first value 2. There is only one element in a complete sample space which takes value 1, that is 1, 1 out of 36. So classical definition of probability says favorable outcome divided by total outcome. So it becomes 1 by 36. P2, probability, chance, variable x taking value 3. P2 means chance that variable x takes a second value, and second value in the range is 3. So how much probability 2 divided by 36? 36 everywhere. Why it is 2? Because there are only 2 outcomes favor to sum 3. Which are they? 1, 2, and second is 2, 1. Similarly, probability x taking value 4, 3 by 36, x taking value 5 with probability 4 by 36, probability x taking value 6 is 5 by 36, probability x taking value 7 is 6 by 36. Now you can see up to 7 probability is increasing up to that. Now x equal to 8, probability is 5 by 36. X taking value 9, 4 by 36. Now it is decline. X equal to 10, 3 by 36. X takes value 11, 2 by 36. There are only 2 outcomes, gives sum as 11. And quite naturally, that is 5, 6 and 6, 5. There are 3 elements, gives sum 10. Quite naturally, 4, 6, 5, 5, 6, 4. Very simple calculations. The last probability number 11, x taking value 12, and there is only one element whose sum is 12, 1 by 36. This is a very good example to understand the concept of symmetry. You can see the probabilities from x equal to 2 till x equal to 7 keep on increasing. And after that, probability keeps on decreasing. So this distribution is symmetric at point x equal to 7. Be remember this example. I will recall this in subsequent topics. Now I want to represent value of x with these probabilities together. That is called as probability distribution. So the ordered pair values of random variable x with respective probabilities. X taking value 2, 3 till 12. Corresponding px, which I calculate, I put below the value of x. You can see up to 7, the values are increasing, and after 7, they are decreasing. Total is 1. So if you draw the graph of these on x-axis, you take a probabilities, and y-axis, you take a value of variable. So your graph will be, it is not a continuous variable, it is a discrete. It will go like this, and then it will fall down. So at this point, that is x equal to 7, probability is maximum. This point in paper 2 is called as mode. So mode is I'm going to teach in the subsequent topic. This is the end of your second example, how to develop probability distribution.